Hi everyone, I'm Xiaoting. Today I'm very happy to talk about our work, FUZZBOOST Reinforcement Compiler Fuzzing. This work is collaborated with Xiao, Lingwei, Chen, Rupesh, Prajapati, and Dinghao. Now let's get started. In today's agenda, I'm going to mainly cover 4 components. First, I will talk about our motivation, and then dive into the method design. Also, I will show some experiment result in our paper, and finally talk the discussion part. Compilers are the components that transfer source code into executables. They are fundamental in the current computing system, as they are part of the trust base of the machine. However, they contain bugs, and it is non-trivial to verify all the vulnerabilities due to their large code base. For example, GCC has about 15 million lines of code, and it is unrealistic for a human expert to verify the correctness of each line of the code. Here are some summarized results about found bugs in those off-the-shelf compilers. And we can see that with the compiler involved, their bugs are also inevitably increased. Such bugs leaves window for the threat, and it's worse for the researchers and the people in industries to pay attention to find these bugs and resolve them. Fuzzing is an effective way to find security vulnerabilities in compilers by repeatedly testing the code with randomly modified or fast inputs. It plays an important role in software vulnerability assessment over decades. To simply put, it is an automatic software testing process to detect unexpected behaviors by executing the program with random inputs. And in the context of compiler fuzzing, no one can exhaustively examine the entire input space in practice. Therefore, a variety of strategies are designed based on the fuzzing heuristics to prioritize finding the interesting inputs to be fuzzed. Such fuzzing heuristics may be a random selection or trying to maximize a specific goal, such as code coverage, executing, timeouts, and crashes. And the coverage-guided testing is widely adopted by fuzzers, which utilize the code coverage information as the search heuristic to generate new inputs from the fuzz action of a predefined list. Fuzz actions usually refer to the code mutations or generations. In this work, we mainly focus on this type of the fuzzing techniques. Although such methods are prominent, there are several limitations. First, these exhaustive searches use the domain-specific heuristics and thereby limited in applicability and scalability. Also, they overlook the benefit from past experience in historical mutations and cannot automatically learn the common knowledge that is shared in different input seeds. Moreover, most coverage-guided frameworks only calculate the rewards after a single mutation is taken, which yet underestimate the power of a series of mutation combinations. In coverage-guided fuzzing, testing coverage doesn't increase linearly. In other words, each of these mutations may not improve the testing efficiency incrementally. If we look into the compilation procedure in compiler, it actually contains multiple checking stages. And those inputs with only one mutation can be rejected by lexical or semantic checks in the early stages of compilation. but a choice of mutations may trigger a giant improvement, as it may increase the possibility of generating more diverse input programs to enhance the code coverage of the compilers. Based on such observation, we formalize compiler fuzzing as a reinforcement learning problem and propose FUZZBOOST. The design of FUZZBOOST is inspired by the fact that fuzzing can be modeled as a learning process with a feedback loop where the model aims to learn the mutation heuristics based on the feedback, which we also call them rewards, from the runtime information for evaluating the quality of the current input. There are some fundamental components in reinforcement learning process. First, the agent, which is the object that observing the current state and takes action for the next steps. The environment, which receives the state and action to produce the reward for this action. In deep reinforcement learning framework, we build a deep neural network to predict the next action. Specifically, we build upon the famous deep Q network in reinforcement learning to develop the framework. And here we show an overview of our designed framework FUZZBOOST. I'm going to briefly talk about it and dive into the details in each part. First, we start with an initial input state, where the choice of P, the choice of a program is not constrained but can be any C program, even not well-formed ones. And we employ the GCC test suite as our sampling pool and randomly select the programs to be our mutation targets. The state extraction means a concrete configuration in the current environment. We can simply consider it as our input seed, which is also a sequence of tokens. And we use a word embedding model to abstract the sequence into a fixed dimensional vector for the following training. Then we use a deep neural network with two hidden layers to predict the next mutation action based on the extracted state. Then we mutate the state program based on our predicted action. After that, we use target compiler, compile the new generated program for the following analysis. Our training objective of deep neural network is to maximize the feedback rewards designed according to our fuzzing purpose. To simplify that, we collect the compilation log to analyze it, and if the seed program can cover new codes or trigger some abnormal crashes, and we will give the model a positive reward. Otherwise, we will give them negative rewards. So like I said before, in this work, we are going to focus on the C programming language and the corresponding compiler fuzzing issues. And in this study, our designed mutations are performed on the token level, which include a couple of designed actions, and those mutation rules conform with the C language lexical requirements, which I will talk about it later. In each training episode, we empirically set up the mutation trees length to be 20 actions maximum to enforce our agent to learn within the short path. Here are like the designed mutation rules. For each of the rule, I will talk about it a little bit. For the insertion, we append the new tokens after the predicted index according to according to the production rules. That is, if the last token is an operator in the program, we randomly sample a token from the existing identifiers as its next. And for deletion, we delete the token located at the predicted index. For replacement, we replace the token at the predicted index with another token randomly sampled from a set of the tokens with same characteristics. For example, if this token in the program is a keyword of the C program, we selected another keyword for replacement. Notably, the keyword and operator token set are predefined, while the identifier token set is generated by parsing the seed program in the beginning. The other type of mutations are to make a change on the current extraction windows. Such designed autonomic mutations include window left shift and right shift, and window size up and window size down with one token length each time. Each of these actions does not change the input program, but motivate the diversity of the extracted substring. After we talk about our mutation rules, now I want to talk a little bit about the key component in our method, the reward functions, which is the key part to get the model to learn how to generate the more valid mutation actions for our fuzzing task. So, because in our goal, we aim to generate test programs that can increase code coverage in compilation as much as possible. And how do we measure the code coverage? There are actually several ways in the literature, and we design a measurement based on the basic blocks in this study. In compiler construction, a basic block of an execution tree is defined as a straight-line code sequence with no branches except for the entry and exit points, which is considered as one of the most autonomic units to measure the code coverage. And in our method, we capture all the unique basic blocks concerning each execution trees and calculate a store of all the unique basic blocks covered by the existing test suite to represent our measure of interest. Specifically, we define such reward function based on the ratio of unique basic blocks covered by a certain fuzzed seed program at step T to the entire unique basic blocks of its mutated test suites I prime along the episode. So the more new unique basic blocks the seed program covers, the more rewards the environment will provide it. And in this work, we mainly compare our design method against one of the most popular coverage-based baseline, the AFL. Here we identify the core differences in the fuzzing design. Like we mentioned, in AFL, they use a random mutation and add newly generated fuzzing programs after only one mutation according to the defined search heuristics into the seed set for the next round of fuzzing. Well, in our design, we learn from a trace of mutations, and similarly, all the programs that have achieved higher code coverage are kept to be the seeds, and waiting for another round of fuzzing, otherwise removed from the seed pool. Here comes to our experimental part. In our evaluation, we randomly sample 20 C programs from the test suite of GCC as our benchmark dataset, and our vocabulary size is 144 tokens. And we empirically set out the window size to be 50. And our model deep neural network include 2 hidden layers. Each of them contains 512 units. And the output of the model is the 8 actions we designed before. Then I will show some experimental results. In this figure, we perform the experiments with our method and the baseline method random-based mutation strategy to fuzz each of the programs from the sampling pool. We respectively generate 1,000 new tests from the seed programs for different strategies and record the accumulated number of unique basic blocks along the execution trees. On average, our proposed method, FUZZBOOST, can achieve higher testing coverage by about 37.14% than the random-based mutation method in terms of the number of the accumulated unique basic blocks on the seed programs. And our trained fuzzing tool learns to constantly accumulate the prior knowledge by training on the seed programs. This actually naturally leads us to the question for the sake of resource cost. Given an agent which is pre-trained on seed programs, can it improve the testing efficiency than learning from scratch? To answer such question, we use the same experimental setting and reuse the pre-trained model based on our previous training to continue the fuzzing testing on the newly generated alpha equivalent test seeds. We also show the results in the figures in these slides. And we can see that the coverage improvement for the case of pre-trained model increase drastically towards the highest coverage against the one trained from scratch. In addition, as the training goes on, the pre-trained model can find useful actions in mutation space more quickly and generate faster programs with high testing coverage. In our design, we hard-code a limit on the length of mutation traces from the computation cost point of view. But theoretically, the trees can be endless to gain enough randomness and achieve higher reward. So the mutation length of one fast program can actually provide insight about if the trained model can intelligently predict the actions to pass early compilation checks and for eligible actions on the search space. Therefore, we did some analysis on how the end state evolves. Basically, we record the distribution of mutation trees lengths and the different training stages. The result is showed in these slides. So we can see from the figure that as the training goes on, the mutation trees lengths are increasing gradually. In this respect, the reward expectation of learned mutation actions are positive in a form that reinforce the model to dig more mutation opportunities in one episode to maximize the fuzzing reward. Here are also some observations about the frequent mutation traces in our results. For one action, for example, the insert token actually the most frequent pattern in such mutation cases. Actually, these patterns share some common parts, such as a model tend to insert new tokens to capture more diverse code space. And this empirical study can also possibly get us for the future study in the mutation rule designs. So here are some takeaways about this, about our work. We review that our insight of leveraging the superiority of reinforcement learning for compiler fuzzing to efficiently solve a multi-step mutation-based fuzzing problem. In our method, we lazy evaluate the mutation result and consider those intermediate states in the mutation traces to explore code coverage in a deeper way. Also, our designed rewriting rules, also the mutation rules, incorporate the structure context of programs. Therefore, our fast inputs can better conform with the syntax requirement of the programming languages. Moreover, our method can be boosted by a pre-trained model. The mutations can realize the comprehensive search in a large space to iteratively get the tool for the future fuzzing process. Okay, that's basically all of my presentation today. Thank you so much for your listening. I am Xiaoting. Currently, I work as a staff research scientist at Visa Research. And here are some information about me. If you are interested in my new work, feel free to reach out. Thanks.